Hello, I'm Jay Hirsch, Director of Administration of Columbia's ERM program. I'd like to invite you to tonight's event, The Promise and Perils of Quantum Computing. I'd like to tell you about some of our upcoming events. On all Thursdays, we have our Exploring the Power of Mindfulness seminars. On Fridays, we have our Coding for ERM seminars. And on Saturdays, we have our IQRM seminars. On October 20th is our next CRO Spotlight series, this one featuring Lakshmi Shyam Sunder of World Bank Group. And in November, we have a panel on operational risk and resilience. And now I'd like to introduce tonight's moderator, ERM lecturer and CTO of Quantum Exchange, Sharyar Shaghagi. Sharyar?
Thank you, Jay. Appreciate the introductions. Welcome everyone, and looking forward for a productive session on a very interesting topic that I think that given the caliber and expertise of our panelists that you'll meet shortly will probably benefit most of you that are in the field of risk management and technology. Just a quick overview of my background. I've been in technology for over 30 years, management consulting with Big Four, and I spent about 6-7 years at Citigroup. I led their technology risk management function, which included information security. During those years, I obviously had the opportunity to work on very large engagements. I was the subject matter expert to Federal Reserve Bank of New York for a number of years. And at the same time, I was also privileged to help in developing the SOC for cybersecurity, or we call it SOC 3, as one of the authors. And I've had a privilege or a good experience throughout the career, and right now my day job as a CTO of Quantum Exchange is to help organizations address their quantum risk related issues or cyber related issues when it comes to quantum computing, and we'll discuss a lot of that tonight. I'm also been involved as a lecturer with Columbia University, as Jay pointed out, for the last 4 years. I teach IT risk management. Enterprise risk management is a graduate or a master's degree, and it's the largest master's program in the world. So with that said, I'll pass it on to Peter Bordeaux, who is one of the very well-established technology architects and thought leaders from a standpoint of quantum research and quantum technology. He heads up that function for Wells Fargo, as most of you, I'm sure you know, is one of the largest banks in the world. And I'm very privileged and thankful to have Peter join us on this panel. So Peter, please just give our audience a few words about your experience, please.
Sure, Sharyar. Thanks so much for that introduction. Yeah, I'm Peter Bordeaux. I'm currently the principal architect for advanced technology at Wells Fargo. I also lead the quantum and emerging technology research and development team. My career goes back about 30 plus years as well. Got my start in electrical engineering, doing research and development work for a number of different large and small companies, including some government work as well. I've done some educational work. I've even done a little bit of audit work as well. I've played in a lot of spaces, and I've been really fortunate to have a lot of great opportunities. So I bring quite a bit of breadth and depth of experience from information security, data center architecture, network architecture, information security, and a lot of different areas. So I've been doing innovation work for most of my career, but here at Wells Fargo, my work is centered on emerging technologies, so horizontal stuff, looking out mainly 2 to 5 years or so. I've written a lot of papers here, technical papers, position papers. I've got quite a bit, a pretty good portfolio of patent applications in the quantum and digital identity space as well. Currently, my team explores mainly quantum technology, so offense and defense, both in quantum computing and in post-quantum cryptography and quantum security solutions. We also get to play in a lot of cool spaces like privacy enhancing technologies, digital identity, extended reality, and some other very cool areas as well. Yeah, so that's a little bit about me. It's a real honor to be here. Thanks, Sharia.
Thank you, Peter. After hearing you being a loyal Citibank client and working for them, makes me want to think like maybe I should join your bank.
I'm not allowed to say that, but I wouldn't mind it. So,
thank you, Peter. So, our next panelist, Roger Grimes. Roger is a well-known thought leader in the space. He has amazing background in technology, as well as quantum computing space. As you can see from his bio on the screen, he has written a number of books. He is currently with Known Before, which is one of the largest and most well-known education, awareness, technology organizations that provides these types of services to various types of organizations. So I'm again very privileged to have you, Roger, on the team, and please say a few words about your background.
Glad to be here, and thanks everybody for attending. I've been doing computer security for 34 years. I kind of think of myself as kind of more the end user representative, or maybe sysadmin representative for this team. And probably my real big focus is on helping organizations try to figure out how to transition from where they are today to the post-quantum world. I've written 13 books, over 1,100 magazine articles. I did write a book on quantum, computing, the quantum threat, and how to do the migration. Just coming out, it'll probably be this week or next week. I was the lead author of the Cloud Security Alliance's white paper from the Quantum Safe Security Working Group called Practical Preparations in the Post-Quantum World, which is really this kind of step-by-step guide about how all organizations should start preparing and getting into the middle of their quantum migration, especially as NIST starts to release their final post-quantum cryptography candidates. Probably a lot of my background is I've been doing PKI and crypto for decades, and I've done hundreds and hundreds of large crypto migrations, but things from like back in the day, DES to AES, if you can remember those days. And more recently, probably 5 and 10 years ago, or up until about 3 years ago, I did a lot of SHA-1 to SHA-2 migrations. So I was involved in helping a lot of companies, large and small, Fortune 500, governments, militaries, move all of the cryptography from here to there. And I'm kind of doing the same thing with quantum. And I really, getting my start in quantum, I was just kind of a quantum geek. Just loved about quantum, and certainly ever since Peter Shor in 1994 said, hey, this quantum stuff's going to be able to break our traditional public key asymmetric encryption. That really, brought my ears up, and I started studying it. So I think I know quantum pretty well, but probably unlike Peter, I don't know any of the math. I'm happy to say that I've never done any of the math. I don't know any of the math. So I know it from more of a theoretical stuff, but I think I can talk about it and explain it pretty well, as long as you don't ask me the math equations. So, but glad to be here.
Thank you, Roger. Looking forward to the conversation. And last but not least, Alireza Shabani. Alireza, actually, I met him on LinkedIn a while back, close to, I guess, about less than a year ago. His background is amazing. I'll let him talk about his experience, but he heads up quantum research for Cisco. If you guys don't know Cisco, which I don't think that anybody is there that doesn't know about Cisco, they're one of the largest technology organizations in the world, and most of the organizations, I'm sure Peter and others that are large-scale enterprise organizations, they're using their variety of their solutions in the networking space, encryption space, and so on and so forth. So really happy to have Alireza join us. And Ali, please go ahead.
Thank you, Shahryar. My name is Alireza Shavani. I'm head of quantum research at Cisco, and it's my pleasure to be part of the panel tonight. Yeah, just quickly about my background. I can say about 20 years I'm in this field. Since my undergrad, I took the first course in quantum computing. Then I decided I should spend my studies in this field that now has become a full-scale industry. And just before joining Cisco, my industry experience, I was part of the Google Quantum Lab early years in 2014 when the lab was started, where I was working both on the application and also mainly on the hardware side and the design of the quantum processors. And after that, I had experience at the earliest stage startup applying AI and quantum computing with the goal to automate design of a small molecule drug. So some experience in pharmaceutical industry. And recently, less than a year ago, I joined Cisco to lead quantum research here, where our program is broad. We're going to develop technology in both area of quantum computing, also quantum internet and cryptography. And yeah, I can say we're maybe the only American corporate, at least we have both program, and would love to share more in this panel tonight. Thank you.
Thank you, and looking forward to it. As a matter of fact, part of our conversation tonight or today, depending on where you're at, is related to applications of quantum computing, and we would love to hear some of your experiences and sharing some of that knowledge with us. So just quickly going over the agenda to level set with the audience from expectation for this meeting. We're going to just give you a quick overview of the threat landscape. This is not just unique to quantum computing, but for those of you who are not very close to risk management or cybersecurity, I think it's a good kind of a tee up. But obviously, the rest of the conversation is all about quantum computers. What are they? Where are they coming from? How are they different from the classical machines? And then we'll talk about some of the benefits as it relates to different applications that quantum machines can solve that our current computers cannot, and talk a little bit about the timeline. Once we have a good sense in terms of what the quantum machines are and can do based on the expertise of our panelists, then we'll go right into discussion of, okay, with all these great benefits, it always new risks evolve, and let's talk about those risks. And I think we're going to focus a lot of our conversation around what are those risks and what are some of the potential solutions that are either being worked on or to some extent going through the evolution of maturity as everything else goes as it relates to managing those risks. And then talk about some of the timelines, especially people like Peter who have a great organization or Alireza with Cisco. What is your timeline? What are you doing? How long have you been working on this? What are some of the key major milestones that you want to share with the audience in case they want to kind of take that as a guiding principle towards that journey? Okay. I think the definition of next generation computing paradigm, the age of quantum computing, we probably have read a lot about, we have probably watched some movies. I remember I saw a movie that bad guys with quantum machines wiped out every data in the world, and we went back 50 years. I mean, the thing is that obviously these computers are real. Major organizations, such as IBM and Google's and a lot of companies outside of the US, even in China and other places, are working in building these machines. There are promises that these computers will be going into production, commercial in the next few years. There's some debate in terms of how many of those few years, 3 or 5 or 10. But the fact of the matter is, it's coming. And with that said, with benefits that we're going to gain, I mean, I'll let the panelists, as we go through discussion, compare the speed of a quantum machine with our supercomputers that we have today. And it's amazing in terms of the differences. But net of it is that when we bring all these benefits, we are going to solve so many problems that we cannot solve today. And that could be, like Ali Reza said, in pharmaceutical, clinical research. It could be in telecommunication. It could be in banking. And it's great to hear some of those examples from the horse's mouth, the audience, the panelists that we have here. But obviously, we have come to realization that with this speed, in the hands of the bad guys, bad things can happen. And one of them, you know, the way we have been protecting our data transmission, any data, sensitive data that governments exchange with one another, or government agencies or commercial space, that data today is encrypted. We've been doing that for the last 30, 40, 45 years or so. But now that encryption key is going to break with the speed of quantum machines. So with that said, that's pretty scary, because the stuff that we are transmitting today can be, through harvesting attacks, man in the middle, can be captured and recorded and put it in some sort of a cheap storage, such as cloud, and then, you know, in the future, be able to access that data. So if you're talking about persistent data, which means data has value over time, we are bleeding right now, and that's something that we need to be aware of. So love to hear about, again, the perspectives related to this type of a situation. But most importantly, what are we doing about it? How are we going to be able to address this issue, which is what we are faced against, not waiting for 3, 5, 10 years from now for quantum machines to come, but the fact of the matter is that our data is in the hands of the bad guys, or can be in the hands of the bad guys today. As a result of that, we need to be able to figure out the strategies related to that. So I think that's kind of the net of the discussion. You know, we've been living in the digital age for a number of years. You know, we're all lucky if you're in the field of technology that, you know, we've been busy. It's a high demanding marketplace. Everything we do in our lives, from, you know, banking to shopping to you name it, right? So the world is evolved around digital transformation, healthcare. So with that said, obviously, you know, the adversaries, it could be nation states, it could be somebody from their backyard, could be with variety of motives. Obviously, you know, you need to understand the motives depending on where you're at, because if you don't know your enemy, how are you going to defend yourself, kind of a thing. We've been able to really put together a lot of cybersecurity programs, and as I'm sure you see a lot of breaches every day, but you also see a lot of programs mandated by government, all the way from the White House here in the US, that, you know, organizations need to spend focused time and money trying to protect themselves, because a lot of these organizations are part of our critical infrastructure. So if a major banks like Wells Fargo goes down, the whole financial system can be impacted significantly. So we are dealing with some serious situation, and the problem is not getting easier. You know, there are 48 billion devices. Actually, this data comes from Ali Reza's company, Cisco, that says 48 billion devices are connected to internet today. And this number is increasing significantly, because everything is becoming more and more of a digitalized, from the stuff that you wear, the gadgets that you're wearing, from the IoTs that's in your fancy buildings, to your automotive, to anything that connects to the internet now is going to become vulnerable. And that kind of makes the attack surface, as we call it, much bigger than what we are used to. So management of this environment is much more complex. And then add on to that the speed of the quantum machines that we know of is going to add a lot more complexity to it. This third bullet is just a philosophical statement, but I like to always say the hackers only need to be right once, while we have to be right all the time. And that's something that we always been against on a defense. I know Peter mentioned about defensive and offensive, and some of the organizations are actually putting some offensive measures in place. Governments have had mixed views about how companies should be offensive or defensive. But net of it is that we need to really understand our threat landscape, and obviously from a cyber perspective and quantum machines, understand what are the risks and start to think about and address it today. It's no time for us to wait until, it's not like Y2K when we knew that the year 2000 is going to come. So we're going to start working on a number of changes to our COBOL programs. I was part of that project for United Airlines back in the days, to be able to really make sure that no planes fall off the sky in the case of United Airlines. Here, if the bad guys have a way of using probabilistic machines or parallel computing and all of these advanced computing systems, they're able to do the damage today. They're not going to announce it that we know how to break it. So that's something we need to be aware of. So with that said, let's jump right into it. I'll start with you, Peter, since you're on the first on my screen. Can you give us a very, in layman's term, very simple definition of, what's the difference between the classical computers and quantum computers, and let the audience understand the basic differences? And then please, after your thoughts, Ali Reza and Roger can add some color to it.
Sure, I'd be happy to. So at the risk of oversimplifying it, one way you can think about it is, while traditional computers or classical computing, as we typically refer to, uses ones and zeros or bits, right? Everything is either a one or a zero. There's no in between. And the power of classical computers typically relies upon how many bits and how fast you can manipulate those bits, and with what accuracy to some degree. And so that's been sort of the benchmark for a long, long time in digital computing. So you can think of quantum computers as having more than just one or zero states. So according to the laws of quantum mechanics, the equivalent of a bit in a quantum computer, called a qubit, has the ability to be a one, has the ability to be a zero, but it also has the ability to be everything in between a one and a zero, right? And so this is the probabilistic nature of quantum computing. So essentially, one way to think about this is, so in a very complex mathematical problem, a traditional computer will take a serialized approach to solving equations, right? One operation, then another operation, another operation, and so on, right? And so some of these problems that classical computers are thrown at, things like factoring prime numbers and things like that, are almost like a trial and error basis. And so that's why some of these problems take, at some estimates, thousands of years for a classical supercomputer to solve. Well, in a way, you could say that quantum computers essentially evaluate all potential or probable solutions simultaneously and provide probable results, or a probability, or what we call amplitude estimation, of what the most likely answer is, right? And so it's sort of like parallel computing on steroids, if you will. That's really, really oversimplifying it, but essentially that's how quantum computers do a lot of the things that they do. And so, yeah, most of the technology that we enjoy today came from this, what I call the first great quantum revolution, right around 1920, 1925, in that time period. A lot of really great thinkers like Einstein and Planck and Heisenberg and Schrodinger developed these theories of quantum mechanics. And out of that, the engineering manifestations of those gave way to things like, satellites and cell phones and laser beams and all of the modern conveniences that we know today. But a lot of the really strange stuff, the quantum mechanical stuff, the stuff that is really counterintuitive, things like superposition and entanglement and all these fancy terms, there was really no engineering manifestation of these phenomenon until fairly recently. And so quantum computing relies on those aspects of that quantum revolution back about 100 years ago or so, that we're just now beginning to be able to exploit in the lab through engineering practices. So that's really what's given rise to what we call the second great quantum revolution, where these strange behaviors, counterintuitive behaviors that are fundamental to nature and fundamental to reality as we know it, are now working for us. And now we can exploit them to do these pretty amazing things. And so, yeah, I'll hand the mic over.
Yeah, you know, one of the things I like to tell people is that all things and all computers actually work on quantum and quantum properties. So even today's classical computers, CPUs, and the way that they create, store, and process ones and zeros and bits really is only possible because of quantum physics, the way that those things work in CPUs. What's different is that quantum computers can actually use and measure and create, store, and measure information using quantum bits, which are, you know, build up. Like, so in a classical computer, you might have electrons or a whole bunch of electrons that stand for a 0 or a 1. But in quantum computers, they can actually use the subcomponents, the subatomic things. They can use properties of an electron to be able to store and create information. And again, just like Peter was talking about, you have superposition, which is that the answer, when it's calculating, it can be all possible answers and not just a 0 and a 1. So the big difference between a quantum computer and a classical computer, again, is a classical computer is still using quantum to work, but they're measuring it at the upper electron, or actually a collection of electrons to stand in for zeros or ones. But at the quantum computer, they're actually creating the circuits, the logic units, the ands and ors and XORs and things like that at the quantum level. So, you know, to make a quantum computer, like this slide kind of talks about, you kind of figure out what quantum particle, elementary particle that you're going to use to create and store information. It could be an electron, it could be a photon if you're going to do something with light. But then you say, okay, are we going to look at a photon, let's say spinning right or spinning left to represent our zeros and our ones? So you've got to pick what quantum particle you're going to start with for your quantum computer. You have to pick the property of the quantum particle. And again, something like spin left, spin right, something like that to represent your zeros and ones. Then you create quantum gates that have the ands, ors, and nots. And there's actually a few more logical gates that you get in quantum computers. And so then you can use those quantum properties of quantum particles to make these and, ors, and not logical gates, and then add problems to it that it can then solve. Let me say, a lot of times when we think about quantum computers, people say, well, they're so much faster. They really aren't mechanically or digitally faster. It's just that they can very quickly solve some types of problems very fast, like factoring large prime number equations they can do. It's kind of, but they don't, like, if you were to tell a quantum computer, add 2 + 2 and tell me what the answer is, it probably wouldn't do it faster than a classical computer. It may even be a bit slower. But what we've learned is that based upon some of those special properties, superposition and entanglement and things like that, some smart people like Peter Shor said, oh, if you give me the properties of entanglement and superposition, I can figure out a way to factor large prime number equations in seconds versus it taking 1 million years. So they're not necessarily doing it faster. It's kind of like maybe you had a chessboard and you're trying to figure out how to move your king from this side of the board to that side of the board. And then all of a sudden someone makes like that Star Trek chessboard where you have multiple layers of chessboards. And now you have more opportunities to get your piece from this side of the board to that side of the board during the game. That's kind of what quantum did. It gave us more possibilities, and that opened up new, unique ways to solve different problems. But you can't just take any problem, put it in a quantum computer and have it done faster. What quantum computers are really cool about is they give you new ways to solve some types of difficult problems.
Great. Ali, you agree?
Yes, so yeah, just adding some more to what Peter and Roger described. We discovered laws of nature, quantum laws of nature, about 100 years ago, and it took us about 100 years just to be able to engineer the system at that level. So we became gradually, we learned the last 3 decades that how to control single atoms and then single photons and how to make them to interact with each other, these bodies, particles. And we started using that level of control for computation. So that allowed us to, to do certain type of computation that we were not able to do before with the more digital computers. And this is a whole new power that basically boils down to two things. One is the coherence or wavy nature of these quantum systems, and also entanglement. That is a non-trivial, non-classical correlation. So we learn how to gradually leverage on those resources to do the type of computation that is not possible with all digital computers.
So can we talk a little bit about the applications of quantum computers, since some of you touched on that already? I'm interested to hear, based on your experience and the role that you have, like Peter in banking and others, forget about the risk right now. Let's talk about the benefits. And we talked about the speed, of course, and Roger did a great job in terms of breaking that down in terms of what it means. But let's talk about some applications of quantum machines when they do become commercial, based on your knowledge. Anybody can go first. Ali Reza, you want to take it?
Yeah, sure. So first of all, this quantum computer, we should have in mind, these are special purpose computers, in a sense that we know, or we expect that they can do certain type of calculations much faster or more accurate. So at the moment that we are talking, or we're thinking the industry, they're not going to replace our day-to-day like laptops or cell phone or whatever computing device that we have. So saying that, we can name few applications that we are some of them confident, and some of them is an area of research. Generally, what it comes to chemistry, design of the molecules, trying to simulate systems at molecules and materials, and that addresses a broad range of industries: pharmaceuticals, materials, batteries. So that's the one area, one application that there are very strong candidate for. When the commercial machine are ready, then we can leverage them to do something non-trivial that we are not able to do. Other applications that are related maybe to banking or other part of industries goes back to optimization. So in certain area, if you have optimization problem, we expect to get advantage from quantum computers or AI and machine learning in general. That's the one area that is a very active area of research to look at the specific application for that. So, and these are very core calculation that we need, and they have a wide application across different industries. So that's make it as a broad reach to industry applications.
Great.
Go ahead, Peter.
Sorry, yeah, I just want to build on that really great information there. A couple things to keep in mind. One of the key things is that a lot of this work is pretty theoretical, right? So in a practical sense, quantum computers have not really accomplished a lot of these things per se. We think they will. We're actually pretty certain they will. And we can prove them, or we can show them mathematically that they will. But the reality is that the evolution of the hardware, the actual quantum computing systems themselves, just is not mature enough, hasn't really evolved enough for a lot of these things to be really practical in everyday use. And so words like candidates for, or we think they're going to be good at, these are key phrases, right? This is a constantly evolving technology. And the other thing to keep in mind is that while we think we know the things that quantum computers will be good at, we're still on a path of discovery. So every time we discover a new algorithm that will run, or we invent a new algorithm that will run on a quantum computer, to some degree, we discover new features that are available on these systems because they're so new and because nobody's really well trained in them, relatively speaking, in classical systems. There's still going to be a long period of discovery of things that we didn't know that they could do, or we thought they could do better, but they can't. So we're still in the trial and error phase here. I think that's really important to remember.
Yeah, the thing I love that, and it's so true, right? It is. I frequently talk about them as sufficiently capable quantum computers, because right now we don't have a whole. We do have probably hundreds of quantum computers, but they're not sufficiently capable yet with enough qubits, enough stability, and other components to do everything we need them to do. But some of the things, like as an example, in chemistry and molecules, the way that I understand it is that today we can follow a molecule, a simple molecule with 8 atoms through about 8 interactions before it starts to become difficult for a classical computer to start to be, to predict what's going to happen next. And the idea is that a quantum computer can take 8 molecules through like 1,000,000 changes, because it's able to predict so much more. Or what's the other thing I heard was something like 79 qubits. 79 qubits is enough room to store like the information of the universe in it. Something crazy with that, like that. But the idea is that you get these scales to be able to do things like traffic simulation. Like we're headed to driverless car, autonomous cars. And we're going to get rid of traffic lights and have cars everywhere in the world speed up and slow down so that they can go through intersections without there having to be stoplights. And you're going to need very powerful computers that are capable of storing and following and doing a lot of predictive modeling for a lot of information. And our classical computers today just don't have that type of bandwidth, but the quantum computers should have that sort of bandwidth. So, and let me say, I just, I've been studying it for 20 years. We are really making some incredible discoveries. We are making more and more discoveries, every month and every year. We're looking at even trying to put quantum on a silicon chip. There's a lot of, China works on that, Australia, New Zealand, a lot of different places are trying to get it to work at a chip level. So, maybe one day they're not going to require these big, environmentally controlled centers, but it's the first time we're going to be able to truly simulate how nature really works. We've never been able to do that. We've only been able to approximate that. So actually having humanity having the power to actually model how nature actually works should lead to a ton of things. And in my mind, I said, we had the internet. When I remember when the internet got here in the late 80s, I remember I was dialing up on BBSs. I was, having my phone dial up, and we were working at 2400 baud, and I could send an email and have it come back in a day, and now you can just say to your phone, what was that Robin Williams movie where he was a clown, and the answer comes back in a second. The internet revolution brought us things that you just couldn't have visualized at the start of it. I didn't know that I would have my music on a little iPod, much less it's now in the cloud and follows me around, and I can talk to my phone, something that Star Trek couldn't even imagine, right? It took a whole spaceship to have, William Shatner ask a question to the computer. I think there's a good chance that 20, 30, 40 years from now, there's going to be some incredible inventions that we just couldn't imagine now because we didn't know the possibilities like Peter talked about. We're just starting to make these discoveries. I really do think that, just in my mind, and I'm just speculating, that quantum computers will be as disruptive to us as the internet was for the past 20, 30 years.
Yeah, sorry, that was
ask, what is your not to cut you off, Peter, please go ahead, but just to add to your thought process, what's your opinion about the timeline of quantum machines becoming common? I know it's not a scientific measure, but something that I'd like to hear from each one of you from a timeline perspective.
Sure. Let me just complete that thought too. That's a great question. So I do want to give an honorable mention, a shout out to non-compute capabilities of quantum technology too. So things like quantum sensors are going to have a radical impact on things like medical device and imaging technologies, as well as navigation systems, inertial and EMF-based navigation systems, as well as timing devices. And so there's a lot of uses for quantum tech outside of just compute, right? And so I just want to round out that field as well. In terms of evolution for quantum computing platforms, many folks have probably heard of Moore's Law. Moore's Law essentially stipulates that there's a linear curve of progression on the power of classical computers over time, to the point where it's predictable. X amount of increase in power over X amount of time, right? And it's very predictable. But quantum computers don't typically follow Moore's Law. And so you'll see radical advances in a short period of time, and then you'll see what we call quantum winters, where months go by and there's not a whole lot of radical advances in the field. So it's kind of more difficult to predict in this field than it is in traditional computing. But, you know, if pressed for a number, I'm going to say that we're probably looking at something like 3 to 7 years for what we call commercial grade universal quantum computers to be able to do a lot of these things that we're talking about today.
Do you agree, Ali Reza and Roger, the timeline?
Yeah, I mean, for a timeline, as you said, it's hard to put exact numbers, but maybe the best would be to refer to the timelines and the roadmap that like different labs and different companies have announced for their progress in coming years, which is between 5 to 10 years. If we put the milestone to reach to 1 million qubit. With the different technology, you know, we can build a quantum computer either by photons, like optical systems, or with atoms, or what electric circuit called superconducting. The timeline sits between 5 to 10 years to reach to 1 million qubits. That then can do interesting commercial calculation with that.
Yeah, let me tell you, I'm going to be a little, I don't want to say paranoid, but I'm an outlier here. I think there's a chance we have a lot more capability than we're aware of. And that's because of maybe Peter called it the quantum winter. 3 years ago, it used to be that all these quantum places would say, okay, we got 40 qubits, we got 60 qubits, we got 72 qubits, you know, and they were, I guess, relatively stable qubits at the time. And we need at least computers with hundreds of stable qubits for them to become sufficiently capable to be doing interesting things. Well, I've got a ton of friends working on different projects, and they're predicting millions of qubits within 5 years. And I'm like, okay. So I have multiple companies thinking they're going to have million-bit qubit computers. I don't know whether it's stable, unstable, or whatever, but it seems to me if we're right now, I think the largest publicly known one is there's a couple around 72. And I'm like, how do we get from 72 to 1 million in a couple of years? There has to be some computers out there, I think, that have more qubits than we're publicly being told about. And I have no sense. I don't know if that is true, but I don't know how we get to 1 million on multiple different platforms telling where we got 1 million on their version in a couple of years, 5 years, and we're still stuck on 72 as being the largest publicly known one right now. That's a heck of a nuclear quantum winner right now that I'm trying to resolve. How do we get from there to there in 3 to 5 years? So it just makes me think we're not being told everything everywhere.
Yeah, I agree. Well, Roger, who is like you know, top of the race, both in terms of sort of companies that you have interacted with or heard of, who is the front of the race, and then also from different nations, obviously US versus other nations.
Yeah, I can't reveal individual companies just because they've shared confidential information with me, but I will say that the names, 2 of the 3 names I know are not ones that you hear traditionally in the media. I mean, they're big companies, but they're not the ones that people talk about. Certainly nationwide, the United States and China are 2 of the biggest competitors, you know, trying to kind of make the race to get sufficiently capable computers and do interesting things. China is probably ahead of us in doing quantum networking, you know, doing different types of quantum networking and what's called photonics. And again, I see Australia and New Zealand. They just do. I see a lot of interesting papers coming out of them about how to simulate and how to create real quantum bits in silicon. So, but you know, I think that the race is certainly on between the U.S. and China, because you'll read about China's committing, you know, $5 billion or $10 billion, and we're trying to get $1 billion or $2 billion. And let me say that, you know, $1 billion in China probably goes 5 times as far as $1 billion does in the States. But there is certainly, you know, I think whatever number you hear about, the 1 billion, the 5 billion, there's a whole lot more going on than even that. Like even just that, I worked at Microsoft for 11 years. They have I think it's 8 or 9 supercomputing centers that are doing quantum research right now. And some of their quantum computers, topological computers, kind of fell through recently, but that's one company with 8 or 9 labs working on it. I'm sure Peter knows a lot about Wells Fargo's working. I think there's a lot of billions in there that we don't know about in a lot of places.
Yep, I agree. Peter, are there any comments related to
Yeah, it's funny. I think a lot of good points were brought up here, Roger, as well. I think to some degree it's a paradox. Sometimes you have to separate the hype from the headlines, right? There are a lot of really sensational headlines, what we like to call clickbait, right? But paradoxically, there's probably a lot going on under the surface that aren't in the headlines. Things that, and as Roger said, developments that people keep very close to their vest, right? And it's important to understand that there's competing hardware approaches, competing approaches to engineering these quantum computers. So photonics was mentioned, which leads to solid state room temperature supercomputers or quantum computers. There's superconducting quantum computers like everybody's seen the IBM and Google machines, right? They look like chandeliers. And there's like all of this amazing apparatus. It's all designed to control these subatomic particles down at the very bottom of the chandelier. And the thing is that the research in the labs, that these little breakthroughs along the way ripple down very quickly to other entities and other research facilities. And so one really great breakthrough in photonics will filter down very quickly to the rest of the ecosystem. And you'll see a huge leap forward in the engineering approach. Right. And so I think we're on the verge of great breakthroughs. We always are, right, in this field. But yeah, I can feel it coming. My spider sense tells me that, yeah, I think even the 5 to 8 year estimate might be a little cynical. We might be on the forefront much quicker.
I agree.
Yeah. So I try to give an unbiased answer because we have our own program working on developing photonic quantum computing processors. But that's more on the future, that which technology we expect to win this race. But I mean, for now, if we're thinking the developments, maybe we can refer to the labs that have been able to show what's called quantum supremacy, meaning that they have a large enough number of qubits and a clean system, clean machine that they can show it's more powerful than a supercomputer. And with that, I think Google and IBM, we can refer, these are kind of, they have reached to that level of development. And of course, China has a very good focused governmental program, and they have a very, very fast development the last 2 years. So yeah, the jury will be out in a few years to see how does this field evolve and different technologies will grow.
Yeah, interesting, because you know, a lot of my students are from China, so I'm sure that some of them are listening, and I'm sure they're happy to hear that their country is doing well in this space. Let's move on to the next situation, or kind of shifting gear from the benefits and if it's real and how many years, to more or less like, you know, the risk, right? I mean, we know every day we wake up, we read articles, or we hear on the news that cyber attacks are continuously impacting our critical infrastructure. We heard about the ransomware attack on Colonial Pipeline recently, and variety of other types of breaches that are constantly focusing more and more on critical infrastructure, including power, energy, utilities, and so on and so forth. So with what we know, and we have been working on, we know that, as we discussed it very briefly at the beginning of the call, that what we have been doing to protect our data transmission is at the risk of quantum attacks when they do arrive. Doesn't matter if it's 3, 5, 10 years from now. And until then, obviously, that data is currently at the risk of sort of being harvested and, you know, being in the hands of the bad guys, so that at some point in the future they can unencrypt it. So what I'd like to hear from each one of you is to describe the problem as it relates to this particular risk landscape, and then, you know, talk about your knowledge in terms of some of the you know, work that has been done in this space to be able to address some of these issues. So I don't know who wants to go first. Peter?
Sure, yeah. So without getting too technical, we have shown mathematically that our landscape of what we call public key encryption or asymmetric encryption, where you have the traditional SSL or TLS connections, that is, so when you shop on Amazon, let's say, and you have like this encrypted tunnel for your financial transactions, that is a very conventional, traditional, almost ubiquitous type of encryption worldwide. That's one very good example of what's at risk. And remember, this is all theoretical, right? We've demonstrated this with mathematical proofs, but nobody's actually broken that encryption yet. We're pretty certain that it will. So, I mean, this is a huge problem. And I think, Shahryar, you nailed it early on. This is almost like a Y2K level event without the luxury of an end date, right? This is a serious business. And it's not just the financial industry, and it's not just the United States. This is a global problem, and it's a problem for everyone. And yeah, and so there's been a lot of work done in this area. So NIST has been, the National Institute for Standards and Technology, NIST, has been evaluating a number of algorithms that are quantum resistant. What they call quantum safe, we like to refer to them as quantum resistant. These are very robust algorithms that run on classical computers that are very difficult, we think, mathematically, for quantum computers to hack or to break, right? So there are a number of classical approaches to this, but that's no trivial task. Migrating to a quantum resilient environment, transitioning to that world of post-quantum cryptography, it's a really big deal. Some organizations spend years just upgrading from one type of encryption to another. So this is not trivial at all. And then concurrently, there are more exotic solutions, more exotic mitigation solutions being worked on, things like quantum key exchange, actually using this quantum phenomenon of entanglement to secure communications, right? So using these quantum methods to exchange keys in a way that almost ensures that they are unbreakable or unhackable, right? Very careful not to use the word never or safe, right? And so, yeah, we're while we're fighting a threat, we're also on the precipice of creating a new level of privacy and security in all of our communications worldwide. So it's kind of like a double-edged sword, actually.
Mm-hmm. Mm-hmm. I totally agree. And I think that, it's based on what you just described, it's a very complex situation and difficult problem to solve because, as you just pointed out, privacy and security, they don't go hand to hand with convenience and everything else that we are getting used to, right? So you're going to have to find that balancing act in that respect. But yeah, Alireza or Roger, you want to talk a little bit about your perspective on risks and how, in your view, it's being addressed today?
Yeah, so maybe I like the way Peter expressed that the quantum technology computing is a threat, but also quantum gives also a solution to us. That's we can use that to build quantum cryptography solutions just to solve the problem with the quantum computing threat. So and yeah, so just to, I think it was mentioned, I'm just reviewing that we expect, we know our quantum algorithms that when we have a larger scale quantum computer, then we can break the current encryption systems, public key encryption, basically, that we use it in a daily base. It's everywhere. Whenever we are connected to internet, basically one of these cryptography algorithm is running behind the scene. So and so as we expect that we're having a quantum computer is the next large enough to break these codes, then right now we have to make a decision or make a change in our system such that for the data that we expect to hold for long term, some of the data, maybe it's related to the personal data about the health or government data, we want to keep them for decades or maybe for centuries. So those data need to be protected now because some adversary can save those data, and 20 years from now, with a quantum computer in place, they can break those. So now I think different nations, we can say, specifically NIST in the US, is leading this effort to standardize these solutions, how we can protect now our data and make relevant change in our security system such that they are quantum safe. So they're not going to be they're not going to be broken in few years. And yeah, so we can maybe in another question we can discuss more about those proposed solutions.
Yeah, before Roger provides his input into this, I know that, I've seen the bar has moved NIST a recent announcement. It was 2024 before those PQCs or post-quantum cryptos are kind of validated or standardized. And then we know that so many years companies like yours, Cisco, would take to be able to take that and apply it against a variety of your technologies and so on and so forth. So we're talking a lot of years to come. And so it's interesting to see from your perspective, maybe Roger, what are companies doing to address the bleeding now, if any?
Yeah. So yeah, real quick, NIST is probably going to release the final candidates probably end of this year, beginning of next year, and have a standard in place by probably a year after that. So it's proceeding really quite quickly. They kind of always said it was going to be between 2022 and 2024, and it looks like they're going to kind of succeed in hitting 2022. And again, the type of encryption that sufficiently capable quantum computers breaks is traditional asymmetric public-private key stuff, like so RSA, Diffie-Hellman, ElGamal, ECC, elliptic curve cryptography, but also it cuts in half the protection of traditional symmetric keys. So things like AES, Advanced Encryption Standard. It also, anywhere you use asymmetric cryptography, like with digital signatures, it also threatens that. We think there could be, because of the symmetric threat, there could also be some threats against some of our hash algorithms and things like that. So that's really what's at threat. It's literally at least 90% of everything we do. Your Wi-Fi works using a combination of asymmetric and symmetric encryption. So your Wi-Fi to get you to the internet, then you're on most connections using TLS, HTTPS and TLS, that's going to be broken. The blockchain and cryptocurrencies won't be broken, but the public-private keys that you use to protect your wallets will be. And people are like, oh my God, you mean they're going to break my Bitcoin? I'm like, don't worry, they're breaking Visa and the international banking system. Like everything runs on it. Even when we talk about, let's say TLS is really a combination of asymmetric and symmetric algorithms, and both pieces have a problem. So we're going to have to replace the traditional asymmetric encryption, but you also have to make sure your symmetric encryption algorithms are sufficiently strong. If you have anything that's like AES 128, you're probably going to make that be, want to make that be 256. But that's the big thing. You brought up the slide, so Peter Shor in 1994 figured out an algorithm that looked like it was going to be able to factor these large prime number equations that were behind a lot of the protection of traditional asymmetric encryption. Then Grover's algorithm came by a couple of years after that and figured out that he could cut the protection of symmetric keys in half. But the symmetric key one's not as bad because we can just increase the key size, whereas in the asymmetric realm, we literally have to invent these new algorithms. And that's the big part. That is really the heavy. If you were to tell everybody that you had to increase your key sizes in symmetric algorithms from 128 to 256, that would actually be a tough problem for the world to accomplish. And then when you tell them, oh, by the way, that's the easiest thing you're going to do, but you really have to replace your asymmetric algorithms on everything, that really is, it's really a tremendous Y2K problem. It's going to be, I think a lot of companies don't realize that within the next couple of years, every single company is getting ready to embark on a post-quantum project that is going to take them years. And it's going to be every company starting soon. And really every company should be starting now.
And since a lot of our students that are in the audience are enterprise risk management students, and risk management is their core focus area, Peter or Alireza, are there methods used today to start assessing the risk within your organization to be able to identify those risks that are potential to quantum attacks in the future? And what are you doing about those risks?
Yeah, I'll jump in real quick and then hand the mic over. So for us, I think in an enterprise as large as Wells Fargo, which is like many enterprises, the real challenge to overcome first is really identifying where the risks are, right? This is a large enterprise. I mean, if you look at just the number of potential endpoints, point A to point B, that we're talking about possibly being at risk, I mean, we're talking about potentially billions of endpoints. So even before you assess the risk or rate the risk or prioritize the risk, first you have to discover where the risk is. And it's almost everywhere, which makes it really crazy. And you compound that with areas that you don't have control over risk, like if you have SaaS providers or vendors, or anytime your data leaves your own premises, there are a whole host of other concerns.
Some of the other areas that, when you look at these NIST PQCs, would that translate into going out there and changing all of my applications to be able to process transactions related to those apps? Or what infrastructure components needs to be addressed from a standpoint of upgrades or changes? So those are some of the huge milestones, I think, that needs to be planned out now, right?
Yeah. So 2 points there, and that was well said. So this is not just a wide attack surface that we're talking about, and it really is, but it's also depthful, right? And we're talking about all of the progressively more complex areas of what we call the technology stack. So from infrastructure and transport protocols all the way up to applications. So yeah, I mean, this problem is wide and it's deep. And so there's a lot to consider in all of that as well. And look, anytime you migrate from one security algorithm or standard to another, there's all kinds of considerations. It's really not lift and shift or plug and play. There's all kinds of considerations and latency concerns and payload size and all of that stuff. So there's really a lot of moving pieces on this chessboard.
Mm-hmm. Yeah, and as you can see from this slide in here, obviously we talked about man-in-the-middle attack and harvest today and decrypt later, and how problems are addressed via harder math, to Peter's point earlier, versus quantum key distribution, QKD we call it, which maybe Alireza, you can give a little definition of what is a QKD, which is
sure. Yeah, so that goes back to the previous conversation that quantum is a threat, but also it gives us a solution. So basically we can use again, we can engineer quantum systems, mainly photons that are like optical systems, and use the property of either coherence, means the wave nature of these systems, or the entanglement, to design a completely new encryption methods that at the very layman way to say that they are secure. The security is given by the laws of nature. As long as laws of quantum are valid, then we expect these new cryptography systems are going to give us a level of security that you cannot match with either with post-quantum cryptography or with the current techniques based of computation. So, but this is a technology under development still. At the hardware level, mainly, there are lots of development need to be done. So, and that's one of the areas that the whole industry is working to build this technology. So the solution that we are expecting for as a threat, as a solution to a quantum computing threat, would be a combination of these post-quantum cryptography algorithms and gradually adding more of this QKD to our the whole security infrastructure.
Yeah, exactly. And actually, you nailed it in terms of, while they each have a different approach, harder math or leveraging laws of physics. I'm actually, part of my day job is to work with organizations to apply the solutions that we've come up with to be able to combine those two concepts into addressing the problem architecturally. And then that's definitely a key approach to be able to really, again, stop the bleeding. So, I think we talked about some of the physics versus math-based approaches as it relates to addressing the problem. And one of the things that I read this morning, actually, one thing I love about my job is that, or the field that we're in, is like, it's not like any information that you just have to continue to refer to. Things constantly is evolving and changing. But relevant to this conversation, I'm sure we know that that Department of Homeland Security, which to our audience, DHS and FBI are the two major federal government agencies that are sort of leading the pack in terms of cybersecurity programs for this country. So they actually made an announcement as early as yesterday, I think, that they basically are giving a heads up that latest alarm about advances in quantum computing technology. I'm reading it from the text that says, as this technology advances over the next decade, it is expected to break some encryption methods that are widely used to protect customer data, complete business transactions, and secure communications. And they're basically giving a heads up that organizations need to realize that, this is real and it's coming, and, you need to address it. But as we shift and we're starting to kind of look at the clock, so we can also address some of the questions. I see some questions out there. But before we wrap up, I'd like to hear from each one of you talking about sort of a journey, or if you talk about the next sort of roadmap. If you have a company or if you're advising companies, what are some of the logical sequence of activities? I know we touched on a few of them, but I think we can just go through some examples of what are your thoughts that organizations need to address starting now.
So maybe I go first. So yeah, I think the very first step would be just going back to the whole security infrastructure that you have inside your IT systems, both for your internal use and also the service that you give to your customers, and trying to find out where are the areas of weakness. So what part of your security system is vulnerable to this quantum threat. So coming up with a kind of starting from there to characterize how much vulnerable you are. And that's basically that would be the first step. And then after that, you can go and look at the solutions that are out there. There are many companies are developing that solutions, offering that. So that's the first two logical step. First, trying to, estimating the threat and then deploying some solution for that.
Right. Roger, thank you, Ali.
Yeah, certainly I think what Peter said, the inventory part, I call it a data protection inventory, like where every company's got to go, okay, what is the data I need to protect? Then what is the encryption that's protecting it? What are the algorithms? What are the key sizes? And let me say that is going to be one of the most difficult inventories ever done, and it will benefit every company that does it, even going forward. But literally trying to figure out where it all is, even in that, like there's applications that people wrote and they left 10 years ago, and we don't even know what encryption is used in it. Third-party providers, it's going to be a major and then you even have multiple levels, like maybe an application is running some encryption, but then the PC or the computer or the device or the database around it runs another. So you're going to literally have to kind of determine the effective encryption, and then so you have to get that all together. So you have to figure out what is your critical data that you need to protect, what is the encryption that's protecting those systems, which ones have to be replaced because we need to keep the data safe long enough, whether it's 1 year, 5 years, 10 years, forever. And then you have to decide, how am I going to protect it? Is it isolation? Is it using post-quantum cryptography or quantum resistant cryptography? Is it using quantum cryptography? Is it using quantum key distribution? Is it using a hybrid system? You know, it's really going to be quite something. But I think that the average company is probably going to spend, you know, probably most of the time in just trying to get the inventory done correctly and accurately. I mean, it is, I've gone through it just trying to upgrade again, DES to AES and SHA-1 to SHA-2. It is a really, really difficult thing to do just for those systems. But then when you say, okay, now we need to look at everything that possibly needs to be protected. And again, even now, there are people that should be isolating their data and keeping it from being able to be sniffed. If you think that, you know, a sufficiently capable competitor might want to look at that data, you know, 3 or 5 years from now, you need to isolate that data, whether it's quantum key distribution or physical isolation, or not allowing it to traverse a network that can be sniffed. There are decisions you need to be making today.
Yeah, it sounds like a lot of work for consultants again.
Yeah, I think it's going to make I really think the Y2K problem is going to look small compared to that, because it's the most incredible inventory. Well, yeah, I guess with Y2K, we had to look at everything too. But you know what, the problem is we just have so much more. Back in Y2K, I think the average company had like maybe 10 or 100 applications. Today, you could have 100 applications on your cell phone. You know, it's just a different scale of the problem.
Yeah, agreed. And you know, like you pointed out, there is a lot of work ahead of us, and while we wait for a lot of these technologies and or solutions to be standardized, there's work to be done now, right? So in terms of discovering you know, the inventory of your risk landscape and being able to, you know, address it today with some potential ways of isolating the problem. Again, another lecture I recently gave on network segmentation and what does it mean in terms of adding, you know, additional layers of defense, you know, defense in depth type of an approach or layered security. So there are things to be done to kind of try to, you know, make the job of the bad guys more difficult. You know, I'm not saying it to, as we all know, as cybersecurity practitioners, never say prevent 100%, but, you know, we can do what we can do to make the job of the bad guys more difficult. This roadmap that you see on the screen is actually an example of a good roadmap to show from, you know, a couple of years ago till the next few years, what are some of the major milestones from discovery, analysis, and all the way through execution. But if Peter, you have anything to add to the, you know, add any colors to this?
Yeah, a lot of great points being made here. And I think just to sort of round this out and add a little color and depth, one thing to keep in mind is that this is not a serialized effort. It's not like you're going to go discover everything and then begin to assess the risk and then begin to mitigate after that, right? So there's some urgency here. And if your organization is large and substantial, like ours is, like many are, you're going to need to do a lot of overlapping. So figure out how to discover your attack surface while you're building your risk models, while you're evaluating solutions, doing your R&D work, so that there's this overlap, right? And so it's all a compressed timeline. The other part that I think should not be understated is education and awareness, right? So these are not really, really simple concepts. There's a lot of complexity on the surface. There's a lot of complexity to the landscape, to the threat, and to the remediation. So this is a big conversation. And sometimes it takes a real focused effort and a lot of persistence to get the awareness, the understanding, the backing, and the buy-in at the top level. So, you know, I think we've done a really good job at Wells Fargo. I think we've done a great job establishing not just the awareness to this, but spreading the word as well. We've published a paper externally at the end of last year, which lays out a lot of this conversation, as well as enumerates a bunch of things that organizations can begin to do now. But yeah, creating that awareness, I think, is the first step. And I think if you haven't already started, I don't want to say you're too late, but you should think about starting now.
Exactly. Thank you. So let's take a look at some of the questions that has come from the audience. Actually, somebody that I know pointed out, because I see some of the names, that Y2K was easy to understand. This is much more complex. So amen to that, right? So that's definitely a correct statement there. Another interesting question, like, do you see the future of quantum computing in augmented reality and virtual reality?
I'll jump in there. So, and not to sidestep the question, but I've been very interested in the application of quantum sensors in virtual reality and in assistance for accommodations for folks with disabilities. So I have a number of visual challenges. So this is near and dear to my heart. Quantum sensors using these subatomic particles and individual particles to create much more sensitive sensors that can detect nano changes in electromagnetic fields and gravitational fields. Yeah, I think we're on the verge of another revolution in the brain-computer interface, which would include VR environments as well. We did actually publish a paper on that also in the first quarter. Interesting stuff.
Any other thoughts, comments?
Well,
Yeah,
I just want to comment. That's trying to visualize how we can apply quantum technology in that space. So quantum computing, maybe, because probably many of these VR, AR, we're going to wear those hardware or applications. So I can imagine how to carry some quantum computer with current technology. But more broadly, quantum technology can have applications when it comes to photonics, sensors, imaging. Those are areas that we expect not quantum computing, but more broadly quantum technology can have some applications. So yeah, if we think very futuristic, we can come up with something with that.
Yeah, and let me say, I'm the opposite of an AI machine language expert. But if we're trying to simulate, if we're actually trying to simulate human capabilities, we are the best quantum computers in the entire world, right? And nature works on quantumness. And prior to quantum computers, we could only simulate at a high level, a very rudimentary level, how real intelligence works. We did not, before quantum computers, we didn't even have the capability of making it work like nature works. With quantum computers, we have the ability to at least simulate how nature really works for the first time ever. We've been guessing. Now we're going to be able to, put problems and go, how would this happen at the quantum level within a human brain? I don't know if it gets us closer to a human brain and consciousness and all that stuff, but I think without quantum computers, you don't get there at all.
Mm-hmm. Yeah, there's another question related to, can we expect a breakthrough in terms of distortions of decision-making process like bias or noise and motivated reasoning using quantum computers as part of like the machine learning algorithms or AI, like some of the weaknesses that AI and machine learning have today with classical machines, being able to have bias or things like that. Do you see that?
Yeah, I'll take that one first. So there's an element there that's near and dear to my heart. So folks might be aware that there's I'll call it a movement around ethical AI, right? Applying these sort of ethical concepts to the development of artificial intelligence and decision-making. Well, as quantum computers come online and become relevant in that space, I think there's definitely an argument to be made for ethical quantum technology applications as well. And one of the things that I love to talk about here is what I call self-fulfilling prophecies. As the probabilistic nature of quantum computers become more and more sophisticated in predicting the outcome of events or even social activities and geopolitical circumstances and things like that, I think we need to be careful that we don't use these predictions to set the course of our own destinies, right? And so there's a pretty interesting conversation there. And I'll leave it at that for the moment.
Well, you know what I wonder about? Like one of the big quantum predictions is we'll be able to do better financial predictions and the stock market people are, but if everybody in the stock market has the best financial predictions, how would anybody ever make profit? If both sides accurately understand it, how do you make any money? Because you only make money, by being able to figure out the inequalities. If everybody has equal information about everything, how do you make any money? But that's a thought for another day.
That was exactly when I answered the question that my girlfriend was asking me the other day about if we could have predicted this or if we had known that, it's, yeah, it's beneficial, but you got other issues. No, I think, in general, we have, based on what I see, have addressed most of the questions. There's one last question. I think we have a few more minutes. There are trillions of dollars spent on refreshing infrastructures and so on and so forth globally. Is what, they're asking, like, what percentage or how much of that money is earmarked towards quantum computing or cryptography? Like, I guess maybe the percentage of the spend as it relates to this area. Do you think it's sufficient? Do you think we still got a long ways to go in terms of, I know that Peter talked about creating awareness, and that obviously needs to, start from the top of the house, but any thoughts there?
Well, I can think about the numbers should be around like tens of billions if we sum up all the investment across the globe. And well, I think that's a good start. Depends how we progress from here, but we expect, yeah. So I mean, I don't want to like put like a specific what's the bar there, but we can see in the last 2 or 3 years we have seen like a good flow of the money in the field, because this is a really technology that has reached to the point it needs industrial level investment, and lots of money should come because it's a hard technology development and it's not possible to do in the universities. So as we show more progress in technology development, so we expect having more investment, both from the private sector and government sector. But just give a number, it should be around tens of billions at this point.
Great.
Yeah, I mean, I think in a status quo world where quantum computing is not a threat, we've got a pretty much flat refresh rate or investment in infrastructure rate, and there's blips along the way. And I think here we're probably looking at something like Y2K ended up being, right? There was some general awareness for the years leading up to that. And then there was this sense of urgency created, and urgency really inspires action, right? So I think we're looking at something that's nonlinear. I think we're looking more like a hockey stick or logarithmic curve, where we'll get 3 or 4 or 5 years into this, and then suddenly there'll be a development. And then there's sort of like this crystallization of, oh my gosh, quantum computers now are like within reach. And then you'll see a lot of urgency in a lot of places, and you'll see a massive, massive push to get this done. I think human nature is kind of that way anyway, but for what it's worth.
But I think the other driving factor could be competitive advantage, or being able to kind of differentiation, right, within each industry.
Yeah, look, there's always a distinction between those players that are interested in the long game and have the fortitude to invest money now without getting an immediate return on investment, right? Looking 3 to 5 years out. And then you've got institutions and entities that are more or less status quo. They go slowly, they creep along slowly. So I think I think you're going to have sort of an organic distinction there.
Exactly. Well, as we are approaching the end of the time, I really want to personally thank every one of you that contributed, significantly to this conversation. Getting flood of text messages as I'm speaking here, that very smart individuals. So as expected, you guys, presented very well and shined in terms of your level of intelligence and expertise in this area. I think that the audience would have the same view. Just for those of you that are interested, the recorded session recorded session would be available soon and distributed to the audience. But with that said, I think we're good to go. And thanks again for your time, everybody, and enjoy the rest of your evening or morning.